This is a screencast for acids and bases with pH, pOH, those type of calculations. So let's begin. The first question on here says, as the acid parts of a solution decrease, what is the effect of the pH of the solution? So this means the acid part. So if your acid part is decreasing, that means that your pH is getting higher. You're becoming more basic. Surprise for most of you. So number 2, the pH of a solution is 13 for this particular question. A pH of 13 means it's in the basic range. Which of the following statements are also true of the solution? Select all that apply. So the solution is basic. We said that because that number is basic. The concentration of hydroxide ion is more than the concentration of the hydronium ion. True, so because it's basic. The solution is acidic. No, that is not the answer. The concentration of hydronium ion is more than, no, because that one goes with that one. It will turn phenolphthalein pink. Yes, if it's basic, it will turn phenolphthalein pink. It will change the color of blue litmus to red. No, that only happens for an acid, so that's not true. It will not change the color of phenolphthalein. That is not true. It will change to a pink. Phenolphthalein in a base always is pink, or that lovely magenta, just like the color I'm writing with. The concentration of hydronium ion is equal to the concentration of hydroxide ion. No, that means it would be neutral around a pH of 7. And the last one, it will change the color of the litmus to blue. Red paper will turn blue in a base. That is true. Moving right along. If an aqueous solution turns pink when a few drops of phenolphthalein are added to it, what is the nature of the solution? Well, it's basic, because phenolphthalein turns pink when you add it to a basic solution. If you add it to an acidic solution, you get no color change. It remains colorless. So a beaker contains 18 milliliters of 0.200 molar sodium hydroxide. Sodium hydroxide is a base. If you put red litmus paper in there, what color is that paper going to turn? Red will turn blue in a base. Next question. How many milliliters of 0.3 molar HCl is needed to neutralize sodium hydroxide solution? We have to write out the equation. So sodium hydroxide plus HCl makes NaCl plus water. So an acid plus base is salt plus water. It's always true. The salt's not always table salt if you don't have a sodium type compound, but an acid plus a base is a salt plus water. And this is a 1-to-1 ratio, so we can use M1V1 is M2V2. We could also call it MAVA is MBVB, where the A stands for acid, B stands for base. I'm just going to plug in the values for the base there because they were together. I'm plugging the first 0.2 molar of the base times 18 milliliters equals M2, which is 0.300 molar, times V2. I'm going to go 0.2 times 18 divided by 0.3, and so the volume is going to be 12 milliliters. The sig figs quite aren't right on there, but that's all right. So the next question is, if there is leftover acid in a separate beaker, what color will red litmus paper turn when dipped into the acidic solution? Well, red turns blue in a base, but if it's dipped in anything else, it will not change color, so it remains the original color. If there's leftover acid and you put red paper in there, red paper is going to remain the original color. So moving on to question 5. A beaker contains 65 milliliters of 0.4 molar sodium hydroxide solution. A few drops of phenolphthalein is added to the solution. What color is the solution? So if you add phenolphthalein to a base, you're going to get a pink color. If you add phenolphthalein to an acid, it's going to remain colorless. So the sodium hydroxide is a base. And how do I know it's a base? Because it ends in OH. Do all bases end in OH? Not necessarily, but if you add phenolphthalein to a base, it turns pink. Next question, how many milliliters of 0.4 molar HCl should be added to exactly neutralize the sodium hydroxide solution in the beaker? So let's write out the equation again. Sodium hydroxide plus HCl is going to make NaCl again plus H2O. They don't necessarily have to be in that order. But the gist of this problem is that it's all 1-to-1 ratio. So we can use M1V1 is M2V2, or you could use MAVA is MBVB. Just find your molarity of the first one, which is 0.4, and times the volume, which is 65 milliliters. And that equals M2, which is 0.400 molar, times the volume, which we don't know. I'm calling it V2 in this case. And how do I do this in my calculator? I do 0.4 times 65 divided by 0.4, so that's 65 milliliters of acid. The next question says, what will be the color of the solution in the beaker at the endpoint? The endpoint means where we ended up, and we said we exactly neutralized it. So if it's neutralized, it's not acidic, it's not basic, it will be colorless. Question number 6. If an aqueous solution changes the color of blue litmus to red and phenolphthalein solution remains colorless, which of the following relationships exist between the hydronium ion and the hydroxide ion concentrations? So blue turns to red if it's an acid. And phenolphthalein, if it remains colorless, what you know is that it's not a base. That if you're working with acids and bases, if it's colorless, it probably is telling you that it's an acid. So the hydroxide is the base parts, the acid is the hydronium parts, which is H3O+, sometimes just H+. So you have more acid than base. Question number 7. Which of the following conditions indicate an acidic solution? So you need to know the pH. In the first one, you are given pH, and it's a 3.01. Anything less than 7 is acidic, so that is true. The second question gives you the concentration of H+. You need to find pH. So you find the formula for finding pH, which is negative log of the concentration of the H+. My pen just doesn't work so well. And that concentration is 4.7 E minus 7, and that gives you 6.3. 6.3 is less than 7, so it's acidic. The next one gives you pOH, and that doesn't quite tell you if it's acidic or basic unless you've memorized that. So what I do is I just solve for pH, and all you do is go 14 minus that number, and it'll give you the pH, and that equals 8.48. 8 is bigger than 7, so it is basic. Letter D, the concentration of OH minus does not tell us pH. We're going to have to do 2 steps to get there. I would find pOH first, because that's an easier way to do it. pOH is the negative log of 2.75 E minus 14, and you hit the equals button, and you get 13.56, and that's the pOH, and now you just subtract it from 14 to get the pH. So 14 minus 3.56 is going to give you a really small number, and a really small number means it's acidic, so that is why that one is marked as true. Question number 8. What is the pH of a 0.131 molar barium hydroxide solution? I gave this one to you because the hydroxide part isn't one part, it's actually 2 parts, so when you see that you have 2 acid parts or 2 base parts in this case, you multiply by 2. If you had a 3, you would multiply by 3. So you're going to take the 0.131 and multiply it by 2. And then you will plug it into the formula to find pOH. Because you have OH, you have to do the pOH equation first. So pOH is negative log of 0.262, and that gives you a number, and 0.581. And then to find pH, you just minus that from 14. So 14 minus 0.581 equals 13.4. And if I were to ask you if that's acidic or basic, you would say it's basic. If I were to add phenolphthalein, it would turn pink. Moving on to question 9. 640 milliliters of hydrochloric acid is exactly neutralized with 530 mils of 1 molar sodium hydroxide. What is the concentration of the acid? We are, again, at the HCl plus NaOH makes NaCl plus H2O. So an acid plus a base is a salt plus water. And it's 1-to-1 ratio. So we can use M1V1 is M2V2, or we could call it MAVA is MBVB. So there's our equation, and again, it's a 1-to-1 ratio. And now I write my formula. This time I chose M1V1 is M2V2. And I chose those numbers that are paired together. So 1 molar sodium hydroxide times 530 milliliters equals the concentration, which I don't know, times 640 milliliters. And what I would do in my calculator is go 1 molar times 530 divided by 640, and that gives me the molarity of the HCl, which is 0.828 in this case. Again, because it was a 1-to-1 ratio. If it wasn't a 1-to-1 ratio, we'd have to put the mole ratio in there. Let's look at question number 10. Oh, I didn't answer that part. It was neutralized, so that means the acid parts, which is H3O, equal the base parts. Moving on to question 10. 100 milliliters of hydrochloric acid is exactly neutralized with 680 mils of 0.3 molar sodium hydroxide. What is the concentration of the acid solution? Same equation. Acid plus base is a salt plus water. It's a 1-to-1 ratio. We could do M1V1 is M2V2, or we could do MAVA is MBVB. It's whatever floats your boat. You just got to keep your like numbers together. And this time I chose M1V1 is M2V2, and for M1 I chose 0.300 molar times 680 milliliters. Those are my base parts, equal my acid parts. M2 I don't know, but I do have 100 milliliters. So 0.3 times 680 divided by 100. So M2 equals 2.04 molar. Question number 11. Consider the unbalanced equation above. Well, it's the same one we've been working with. It's still 1-to-1, so there's nothing we need to do to it. What volume of 0.28 molar HCl is needed to react with 29 mils of 0.12 molar sodium hydroxide? Again, an M1V1 is M2V2, or MAVA is MBVB. So the 0.12 molar times 29 milliliters equals 0.28 molar, 0.280 molar, times V2, which we don't know. And in my calculator, I will plug in 0.120 molar times 29 and divided by 0.280, and that's going to be 12.4 milliliters. The next question is a change up. We have sulfuric acid plus sodium hydroxide makes sodium sulfate plus water. It still is an acid plus a base is a salt plus water, but now we don't have a 1-to-1 ratio. If you go through and balance this, we actually have a 1-to-2 and a 1-to-2 ratio. So it goes 1-2, 1-2. So in this one that is a 1-to-2 ratio, I got to go very fast because I actually don't have much time left. It's a 1-to-2 ratio. We write down what you know of each part. Those are the acid parts. Those are the base parts. I chose MAVA is MBVB. I plug in my parts. Volume of acid, the molarity of the acid, the volume of the base. And then I had to plug in this mole ratio. There's 2 NaOHs from up there to 1 H2SO4. That's where the 1-to-2 ratio comes in. I do 0.230 times 82.5 divided by 2 divided by 74. And I get this molarity for the acid.